Hello everyone, this is Dr. Sulaiman Khan and you are watching my YouTube channel The Beauty of Mathematics. Today I would like to discuss about the Legendre polynomials. Legendre polynomials. As in our previous lecture, we have derived the general solution of the Legendre differential equation while using the power series method. We have find the general solution by using this technique, which is equal to a naught plus a1x plus a2x square plus a3x cube plus a4x4 plus up to so on. So we have simplified this and we have derived the general solution a naught into 1 minus n into n plus 1 n plus 1 divided by 2 factorial x square plus n minus 2 n into n plus 1 n plus 3 divided by 4 factorial x power 4 plus up to so on and plus a 1 time x minus n minus 1 into n plus 2 divided by 3 factorial into x cube plus n minus 3 into n minus 1 into n plus 2 into n plus 4 divided by 5 factorial and x power 5. This was the general solution of the Legendre differential equations. So now we will try to derive certain Legendre polynomials from these equations. We have also discussed the recurrence relations for the Legendre recurrence relation or recurrence formula. We have discussed already in the previous lecture. So now we will use by Legendre recurrence relation Legendre recurrence relation. We have AR plus 2 is equal to minus time n minus r into n plus r plus 1 divided by r plus 2 into r plus 1 ar, where for example this is 1, where r is equal to 0, 1, 2, 3 and so on, and n is any real number. N is any real number. So now we will derive the coefficients of these coefficients while using this formula, and we will check the Legendre polynomials. When n is equal to r, that is n is equal to 0, 1, 2, 3 up to so on, is because r is also equal to 0, 1, 2, 3 and so on. So then we can get from equation 1 a r plus 2 equal to 0, because when n is equal to r, so this term can make the whole because this term will be 0 and this whole multiplication can become 0, so the right side will be equal to 0. This is equation 2, and this can be happen for any n is equal to 0, 1, 2 and 3 and so on. So now we will check for n is equal to for n odd or even. So if n is even, then y1 of x becomes a polynomial of even degree, becomes a polynomial of even degree n. This value, this is y1, because this solution we can also we have reduced this to the form y is equal to n art y1x plus a1 y2x. So when n is even, so we can get these are the even terms, so we can get y1 a polynomial of even degree. And now we will see that how. For example, if we consider for the case when n is equal to 0, so equation 2 can become n is equal to 0. So it means r is equal to 0 because n and r both are the same. So a2 coefficient will be 0, which implies that the other coefficients over here with the even terms will be also equal to 0. This can imply a4 equal to a6 equal to a8 and up to so on. All these even coefficient will become equal to 0. So when this is the case, so and hence y1 equal to, and hence y1 of x will become equal to 1, because the other coefficients are equal to 0, so only y1 is equal to 1 is left, which is we can check we can put these values the values of a2 a3 a4 a6 in the general solution, and we can get this one, which is a polynomial of of 0 degree, because we have taken n is equal to 0, so this is also 0 degree polynomial. uh, and if we check it for f n is equal to 2, then the equation 2, the coefficient in equation 2 can become a 4 equal to 0, which can implies that a 6, a 8, a 10, up to so on, all of them can become equal to 0. And hence y1 of x will become 1 minus 3x square, which is a polynomial of degree 2, or n is equal to 2. So similarly, if we take uh, if n is equal to 4, then equation 2 can become a 6 equal to 0, which implies that uh, a 8 is equal to a 10, a 12, and all the rest of even coefficients can become equal to 0, and hence y1 of x becomes as y1 of x is equal to 1 minus 10x square plus 35 divided by 3x cube, or this can be written as 1 by 3, 35 x cube minus 10 minus 30 x square minus plus 3. So this is the Legendre polynomial of order 4. Order 4. This is so this is 4, not 3. So this is the case. Y1 is equal to this, which is a polynomial of degree 4, and if we continue this for the odd degree, so what would be the result? If n is odd, then y2 reduces to a polynomial of odd degree n. The other solution, which is in general solution, y is equal to nr to y1 plus a2 y2. In y2 the powers are odd, so this will be an odd degree polynomial of degree n. This will be a polynomial of degree n, where n should be some odd number. So to check this, for example, uh, n is equal to 1, we can reduce the equation 2 become a 3 is equal to 0, which can implies that a 5, a 7, a 9, up to so on, all these coefficients can become equal to 0, and hence the y2 should be equal to x. While putting these values in the general solution, which is a polynomial of degree n, a polynomial of degree n, where n we have taken in this case 1. So similarly, if we continue for n is equal to 3, then equation 2 can become f5 equal to 0, and this implies that a7 and 9 up to so on, all the rest of the coefficients, odd order coefficient, are equal to 0, and we get y2 will be equal to x minus 5 divided by 3 x power 3, which can be written as 1 by 3x minus 5x cube, which is also a polynomial of degree 3. So these are some examples we have taken for a few specific cases, and now we will try to find the general Legendre polynomials of degree n. Legendre polynomials of degree n. So Legendre polynomials of degree n. The Legendre polynomials is, we have already discussed that the Legendre polynomials are the solution of Legendre differential equations for a non-negative integral value of n are called Legendre polynomials of degree n, and these polynomials are denoted by Pn and can be defined generally. Pn of x is equal to summation m is equal to 0 to capital M minus 1 power n minus 1 power m divided by 2n minus 2m factorial divided by 2 power n m factorial n minus m factorial and n minus 2m factorial. This is, for example, equation A. So where the capital M can be taken by the form where capital M should be equal to n divided by 2 or n minus 1 by 2. Any one in these two, we get an integer, so that will be the required or the desired value of capital M. So now we will generalize this summation. We can take Pn of x is equal to, when m is equal to 0, so this expression can become here also one term, another term is x power n minus 2m, n minus 2m. So we will simplify this summation, and we can get uh, m is equal to 0, 1, 2, and 3, and so on. So we can get this like 2n factorial divided by 2 power n, and n factorial square x power n minus 2n minus 2 factorial divided by 2 power n minus 1 factorial into n minus 2 factorial x power n minus 2 plus 2n minus 4 factorial divided by 2 power n 2 factorial n minus 2 n minus 2 factorial n minus 4 factorial and x power n minus 4 plus up to so on. We can expand this summation, and now for n is equal to 0, for example, we have to put n is equal to 0, so we can get p naught of x when n is equal to 0. This is 0 factorial, which is 1, 2 power 0, 1, this is also 1, so we can get x power 0, which is also 1, so we can get p naught of x is equal to 1. For n is equal to 1, we can get x power 1, and this is 2, this is 2, this is 1 square, so this can be cancelled, and this is 0, so we can get p1 of x is equal to x, and for n is equal to 2, we can get, while putting the values of n 2 in this expression, in this series, and we will get 1 by 2, 3 square minus 1, where n is equal to 4, we can get this polynomial 1 by 8, 35x4 minus 30 x square plus 3, and for n is equal to 5, we can get this polynomial 1 by 8, 63 x power 5 minus 70x cube plus 5x, and so on. So we can get any degree of polynomial from this expression while just putting the values in this expression. So these are called the Legendre polynomials of degree n. Thank you so much. See you next time.